What energy Compton has? Go ahead.
2/3 of the initial energy.
No, like the initial, not the secondary photon.
Oh, 20 to
40, right? And what I said to remember this, right? Compton, boys in the hood, dangerous. It shoots at you, right? Right? It shoots at you, so it's occupational dose, correct?
Mm-hmm.
All right, remember that. And then classical, way you can remember that, classical singing and vibration, right? So what does classical work with?
coherent. Oh.
How does classical work?
Oh, how's classical work?
Oh, it hits the.
Go ahead, Jay.
It's no loss of energy. Hits outer shell and then just slightly goes away.
Does it knock out the outer shell?
No, it's agitated.
Yeah, it vibrates it, right? You know, classical singing, vibrating, right? Awesome. And then what happens with classical? Doesn't it occur most of the time?
Because inherent filtration gets
Inherent
rid of it.
filtration, because it's less than 10 keV, so it gets filtrated, okay? Awesome. Anybody have further questions? Everybody? Yes, Mr. Black? Dr. Black? My apologies.
If I was holding a patient in the x-ray room, am I exposed to Compton scattering, or am I exposed to characteristic of what kind of radiation am I exposed to?
If you're holding the patient?
If you're holding the patient?
Right, I'm in the room holding a patient,
Yes, sir.
and so you make that exposure, so am I more prone to be, what type of interaction am I more prone to be exposed to?
Compton.
Compton
Like
scatter.
in general, but Compton.
And why Compton?
Compton, because it redirects. Well, it causes a lot of scatter. So all scatter is bad radiation, and so you get exposed to that Compton radiation. Does that answer your question?
So where would I find that information?
In the book.
This Donahue dying back there.
Mr. Don, you want help? So you can find this information in the book or PowerPoints. You know, we can go over it again. I can retweet it.
But I thought the photoelectric effect is when I absorb it more so compared to Compton. And I thought photoelectric was more scattering in the forward direction compared to Compton.
Photoelectric, more.
Photoelectric is the patient absorbs it.
Yeah.
So it doesn't scatter.
But we're behind the patient, we're holding them.
No,
So-
you would be
Behind
behind
the
the
patient,
patient because you would be in front of the IR, so why would you be behind the patient?
If we're holding the patient, even if we're wearing lead shielding, you're still gonna get some of that scatter because it's side scatter, back scatter, all that stuff.
But
So
you
that's-
said photoelectric. She
Right.
said it's a-
So it
that's
says
absorbed.
up there, patient dose impact, interactions, deposit dose. In coherent, it says not significant for patient dose, and then down on Compton it says electrons deposit dose. So I'm just assuming that it's, that's what the question was referring to.
We're not near the patient, and we won't even get radiation.
He was asking if we were behind, like near the patient, holding the patient. Why?
Near the patient.
But that's occupational, like that's when you're sort of away from, like that's backscatter.
Compton is occupational.
Right.
That's a good question to look up there.
We'll search that. Can someone write that down? Can someone write Mr. Black's, Dr. Black's answer, question?
I can look the answer up.
We can look it up, yeah.
But the trap, don't be on
I
your
like
phone.
that y'all trying to work together though. Team effort, find the answer.
Or is this connected to the slide or the PowerPoint from Friday or?
It's a little different.
Oh, okay.
What slide are you looking for?
The one for Friday.
Cause I was gonna ask, cause I forgot to put the different name for the classical.
Oh, we have it right here.
Okay.
And the reason I also ask you the question is because everything is about critical thinking. And so if the board asks, they're not gonna ask you direct questions about what you learned on the slide, but they're gonna ask you to critically think what's gonna happen if you are in a room holding a patient. How do you critically think is going to be, what are you gonna be exposed to? Photoelectric, Compton, paraproduction. Is paraproduction in the scope of things too?
Yes, sir. We haven't went over it, but we're like going over it. Yes, sir,
Oh, okay.
today.
Was Rayleigh's scatter Also known as classical. Is that another name for classical?
No. So all these are all classicals.
The word was Rayleigh's then.
Radius.
Yeah. Like R-A-Y.
Classic from here.
It was. I think it was another slide.
It was in this,
I don't have it written here.
it's right here.
Okay.
Classic.
Rayleigh? Okay.
Yeah.
Okay.
So before we move
I just
on, does
remember
anyone
hearing that.
have extra questions for classical or Compton scatter?
Do you know what I understood was that the Compton scatter is the one the people in the room will get that, did I get it wrong?
You saying
But,
for scatter?
But it says in this Compton interaction over here, the secondary photon, when I was reading this, I'm not very clear about it, but it said that the people in the
In the
room
room?
get the second one.
Yeah, so
Scatter, they get.
yes, anything that's scattered, it affects the IR with bad image quality, and it can reduce, it occurs with occupational exposure as well. So again, so the X-ray photon, what is the initial X-ray photon called? The incident photon, correct? And it hits the matter, and it creates a scattered photon, or it can be also known as a scatter photon, which reduces IR fog or occupational exposure, correct? So yeah. Okay, so we're gonna go on to where we stopped off last. So this is where we stopped off last Friday. Okay, guys. So this is everything new. So photoelectric absorption, right? Main common factors. You gotta know the energy level. This is something you just have to know. It's 20 between 120 kVp. Okay, and the interaction is between K and L. So which one has a stronger binding to the nucleus, K or L? K, correct. Because why? Okay, perfect. And so the energy from the photon is absorbed by the electron. And what does that mean? You know how in Compton, where you hit the electron and then 1/3 gets absorbed, but 2/3 gets released, right? Everything gets absorbed in this one, correct? And then the energy is higher than the binding of the electron. That's the reason why it gets ejected, right? So what happens if the incident photon doesn't have as much power as the orbital electron? What happens? Does it knock it out, or does it just stay its place? Its place. But if it's higher energy, what happens? It knocks it out. Correct. Perfect. So we can just keep writing this. But as you can see in the GIF right here, the X-ray photon, also known as the incident photon, it hits the K. Is it K? Is it K or L? That's L. Sure. See, okay, that's K actually. Right? It hits K and it knocks it out, right? So that's photoelectric absorption. And just let me know when everyone's done writing. You okay? Everybody go on this one? Yes. Yes, sir?
So was this the answer to Dr. Black's question?
I don't believe so. I don't believe so. Was it an answer?
I asked a question.
I'm a little sweaty, so. But I don't believe so. I would say it's Compton.
It is.
It's
Because
Compton.
it says the
Compton.
photoelectric is completely absorbed by
Sure.
once a day by the patient.
Okay. Awesome. And then everybody's good?
So the electron absorbs it and it gets kicked out?
So when it says absorb, you know how in Compton, when it came in, it hits, and then 2/3 of the energy gets taken away. So it just completely absorbs, so that number won't be no more. It should be gone, right? Does that make sense?
The photon goes away or the electron goes away?
The electron. Cell's empty. We can keep going forward. It explains more in the future slides. Okay, so photoelectric absorption, the ejected electron is known as the photoelectron, right? So the one that gets ejected, that's the photoelectron, right? Just to let you know. This can interact with other atoms, correct? So that one atom that gets sent flying, that atom can interact with other electrons, causing other interactions. So it gets sent from the traditional atom, gets sent flying, and it hits another electron, correct? And this does not contribute to the radiography image, because all of it gets absorbed, correct? Unlike Compton, not all of it gets absorbed. That's why it leads to fog. But since it's all absorbed within the body, it's not able to cause any misleading It's not allowed to interact with content, okay? And do you know why this can increase patient dose? Say that louder.
Is it because all the energy is being
Absorbed, right?
Yeah.
So, yeah. So if it's all absorbed in the body, that's where the patient dose is occurred, right? And then when Mr. Phung comes in, I have him describe this math for you.
Is he gonna go back over it?
Yeah, he's gonna go back over it. When he comes in, he's gonna help you guys out. Hmm? He said 20 minutes, but he should be here shortly, very soon. Yes,
What are
ma'am?
y'all trying to say to the poor man up there?
No,
Yup.
because Mr. Phung is really, really, really good at breaking every single thing
There you go.
down.
So what
For
y'all
all
trying
of
to say
us.
to this poor man up here?
For all of us.
He's doing good.
But he's doing good.
He's an educator right now.
You're doing good.
You are doing good.
I think making him nervous.
You're glistening.
Just ignore him.
In the
I
classic,
need some toilet, some tissue.
Think
Yes,
you're
ma'am.
messing up productivity.
Yes, ma'am?
in the classic injection, it said that because energy is not too much, so it stays in the atom only. And how is that different from photoelectric absorption?
For electric absorption?
The classic, when I was reading the classic, what it taught us yesterday, it said because the energy is less, so it hits it attacks other atoms in the.
So what the difference between classical and photoelectric is that classical, since the energies are so low, there's a chance of not occurring because it gets filtered. But let's say if it passes, it's only going to excite the electron because it doesn't have enough power to kick it out. Make sense? But with this, since it's between 20 to 120 kVp, it has enough energy to knock out those orbital electrons, correct? Okay. So on to the next slide. So yeah, ejected electron leaves a vacancy in the inner shell, right? So what usually happens when the MVP I was looking for?
The cascade effect.
Now, where does the cascade effect happen?
In the tube.
In the tube. So why would the cascade effect happen? No, it's a good question. No, that's what I thought as a student. You know, when I was first learning this, I thought the cascade effect would happen here, but it doesn't occur in the human body, correct? It's only in the tube. Those two interactions.
But the outer shell electron will fill the vacancy.
Yeah, most of the part. Yes, most of the time. And then, let's say the K shell gets knocked out. What would happen? Would it just repopulate one, or would one of the other orbital electrons knock down and fill up the gap? What would happen?
L shell will come back.
L shell would happen, but rarely other shells can fill it up too. It just depends.
So you said this is not the cascade effect, or it's a different form of cascade effect?
Yeah, but it's still filling outer shell.
And it's still producing
It's
photons.
still filling it, but it's not the same.
It's still
process.
producing
Right.
photons, so.
So yes, so this is basically your characteristic cascade from the target. The main difference between this and your characteristic interaction is that what sets off this photoelectric absorption interaction?
The initial shot.
What comes in and sets off this entire process?
Initial photons.
Incident what?
Photon.
Photon. What sets off your characteristic interaction in the tube?
Electron.
Incident.
Filament
Electron, right, the filament electron, right? So that's your big difference between this versus your characteristic interaction in the target. Right, both of them deal with that inner shell electron, both of them knock it out, both of them end up with outside electrons filling. But it's what starts off the reaction that's going to be different.
Test question.
Okay. Second big difference between them, in the target, what atom are we dealing with when we have our characteristic interaction? Tungsten, great. Does the body have tungsten?
Not usually.
Not usually. Okay, right. Maybe you have some orthopedic implants with tungsten, right? But normally you don't have tungsten in the body. What do you have in the body? Right, you've got your soft tissue, right? So you've got things like carbon, you've got things like calcium, you've got things like oxygen and hydrogen, right? Much lower atomic numbers. So the K shell is going to be much lower in terms of binding energy, right? we're not going to see that 69.5 keV binding energy in the body like you see in your tungsten atoms. So the energies we work with here are also going to be much lower. Does that make sense?
Yes.
Right? So you don't need a 69.5 keV electron, or sorry, 69 keV photon to set off photoelectric absorption, right? It just needs to be higher than the energy of the K-shell. And in the body, the energy of the K-shell is going to be much lower.
Around 10. What's EV? It's will be KV.
Great. So you notice here, right? The release of energy from our so-called characteristic cascade here. 10 what?
Electric volts.
EV. That's right, it's not even KEV anymore, right? It's just EV.
Just because it's that small?
Right, because the binding energies are that low. That we're not having big jumps in terms of KEV. They're very small changes. They only give off EV. So are these 10 EV photons gonna leave the body and expose you?
No.
No, they don't have enough energy to do that, right? This energy is going to do what? It's going to stay,
In that
right, stay inside the patient. It's going to be absorbed by the patient, right? Last bullet point, right? These photons are absorbed inside the body, right? So, last time we talked about Compton interactions. What kind of dose did we say is primarily attributed to Compton interactions? Right, remember, Compton scatter, so what kind of dose? Whose dose?
Ours.
Right, our dose, right? Compton scatter is responsible for our dose. But with photoelectric absorption, whose dose do you think that's responsible?
Patient dose.
So, with that, now back to my question. You should be able to answer that question. The question was, if you were standing in an x-ray room holding a patient,
Yes, sir.
and you were exposed, are you being exposed to photoelectric absorption, or you're exposed primarily to contact?
The Compton. Compton.
And why is that?
Because
would be absorbed in the patient.
Photoelectrics is absorbed
So-
in the patient, most of our doses, as
Compton.
the professor here says, it's coming from contact.
Yes, sir.
Right, very good job, right? So bringing everything together, right? Don't look at all of these as individual parts, right? When we're learning, yeah, we can kind of try and think of it that way, but our end goal is to think of everything together, right? How all of that is coming together inside the room, because it's not just one or the other, correct? All of this is happening at the same time inside the patient. All right, very good.
Alright, on to the next slide. Any further questions? Everybody good? Get the question? Question ready? Writing down. Okay. Okay, so the cause again. So how much energy is this usually? 20 to 120 kVp, right? And then what shell is it mainly affecting? And what are those two inner shells called? Or what not? KNL, correct. Okay. And how much of absorption is it? Is it 1/3, 2/3, all of it, 20%? All of it, right? Because it leads to, this is the main factor of patient dose, correct? And the way I like to remember it is just absorption. That's the only one that has absorption in it, so patient absorption. So, all right, on to the next. Yeah, so like what Mr. Phung said, the atomic number is completely different than we will find in the tube, right? So tungsten has the set numbers, right? 69.5 and so on. But in the human body, we have skin, calcium, all the atomic you can think of, all of them have different types of binding energies. That's why when you increase the atomic number, what is mainly absorbed? Bone, tissue, or fat? Bone, right? Because bone has a higher atomic number, right? So that's where mainly of the absorption is going to happen, right? And then, go ahead, Mr. Phung. You got anything to say?
All right, so this part is very important, right? I need you to pay attention to the two factors that affect photoelectric absorption, and I need you to be able to contrast them with Compton interactions. Okay, we talked about this last week because they are very different. So what two factors do you see here affecting photoelectric absorption, or Sindhu? What are the two factors that you see?
So that's increasing the atomic number.
Atomic number?
And then the decreasing the incident photon energy, decreasing the energy of photon.
Energy of the photons, energy of the X-ray beam.
And so does anyone know what that means when it says decreasing incident photon energy? Can anyone give a great guess on what that is? Go ahead, Joe. KVP, you are correct. So whenever we do lung X-ray versus rib X-ray, which one would have a lower KVP?
Lungs.
No, it would be ribs actually, because the main focus is to see the ribs, right? So if you have a lower KVP, that means you have a higher chance of absorption, correct? So that's why we use lower KVP when we want to see bones, right? Because that's where it mainly will be absorbed instead of shooting straight to the bones, correct? What do you think, Mr. Phung?
So does that make sense?
Okay, I can break it down.
Yes, Jay.
So this is kind of side, but is this going to go into a radiation weighing factor, or like?
It does not.
Okay.
Radiation weighting factor, and this is a little bit advanced, we'll talk about this later, but radiation weighting factor depends on the kind of radiation. So X-rays, like we're dealing with right now, versus gamma rays, versus alpha particles, versus beta particles, versus neutrons. So that is what radiation weighting factor, that is what will affect your dose, right? Depending on what kind of radiation you're exposed to, different types of radiation give you different amounts of dose. So no, right now this would not affect the radiation weighting factor. Okay, yes, Reagan.
Does this have something to do with photoelectric absorption?
This here?
Yeah.
This is about photoelectric absorption.
Okay.
This is how likely photoelectric absorption is to happen. So I want you to just think about your X-ray. So when you shoot an X-ray, what shows up white, what shows up black?
Bone shows up bright and
Okay, bone and metal is white, air is black. Very good. Okay, so when something shows up white, what happened to those X-rays? Did they go through the anatomy or did they stop?
they are radio opaque. So
They
they're-
stopped. Great, the object is radio opaque. If you see something black, did the X-rays go through the anatomy or did they stop? They went through, radiolucent, correct? So, something which is radio opaque. So we just said bone is an example of something radio opaque, right? Bone has what? A higher atomic number. So as atomic number increases, we have more absorption, more X-rays stop inside the tissues, and so the area looks more white. Does that make sense?
Yes.
So photoelectric absorption is responsible for determining whether an object will be radio dense or radio opaque or radiolucent, right? The higher the atomic number, the more photoelectric absorption we have, the more radio opaque that object is. Okay, are we clear on that?
How do we measure one thing's atomic number?
Atomic number, in the book you'll see some estimations as to different tissue atomic numbers. So soft tissue versus bone. We might also have a slide later on with that. Now, KVP. What is KVP, Veronica?
Quality.
Great, it deals with beam quality. Reagan, what else does KVP deal with? I'm looking for the P word. What the hell is it? Penetration, great. Monsi, what does the word penetration mean?
It means that the beam is able to pass through the anatomy.
Beam is able to,
Hit the ion.
great, beam is able to pass through anatomy and hit the IR. Give me one moment. Melanie, if the beam is able to pass through anatomy and hit the IR, Was there absorption? No. So as our KVP increases, what happens to the ability to penetrate? It increases. So as the ability to penetrate increases, how much absorption do we have? Less, decreases. So energy is inverse to absorption, right? Absorption decreases inversely with energy. As energy goes up, absorption goes down. So you have more penetration, you have less photoelectric absorption when we raise the energy of our beam. Yes, Jay? Okay. Yes, Charles.
So, just to get a clear understanding on it, the lower photon energy and the higher atomic number, that means the probability of this occurring is higher.
Very good.
Yes.
So let's take what Charles said and think about this practically. If I want to make bone show up in stark contrast to my tissue, right? So I want bone to show up white, I want other stuff to show up black, right? I want my bone to show up nice and white. Do I want more absorption or less absorption? I want more absorption. Great. Can I influence the atomic number of my bone?
No.
No. Can I influence the energy of my beam?
Yes.
How would I change the energy of my beam to make the bone show up better?
KVP using
KVP will go which way?
Decrease.
Decrease. Why decrease?
Because you want,
So-
You don't want it to
you
pass
want the
through.
energy, the photon of the energy to be,
You want it to
to
absorb.
be, less.
Right.
Yeah.
We want the bones to be able to absorb the X-rays. If we decrease the energy, it becomes more likely that the bones will absorb the X-rays. And so the bones show up more white. Does that make sense?
Yes.
Right, so if we want to make bones the highlight of our image, we actually decrease the energy. That way the bones absorb more.
What does it mean by to the third power
Mm.
of X-ray?
Yes, so the amount of absorption changes by a cube. So if you change the energy by a factor of 2, the amount of absorption changes by a factor of 8.
So it's.
Right, so
it's
my
easy.
KVP goes from 100 down to 50, right? So I changed my energy by a factor of 2. The absorption goes the opposite way, right? If I went down in my KVP, absorption goes up by 2 cubed. 2 to the third power. 2 times 2 times 2. So the amount of absorption goes up 8 times. The bone absorbs 8 times more X-rays when I drop my energy in half. That's what this means here. Yes, Jamaica.
Okay, can you repeat the process when you said, we want photon energy to be less, we want to, the bone to absorb energy?
Mm-hmm.
So will we decrease the KVP and the energy?
No,
KVP
it's
is-
KVP is energy.
Oh,
So think of it like this: if KVP is higher, the more of a chance it has to shoot straight to the bone, right?
okay,
But with the lower KVP you have, the more of it not passing completely through the body, and
Okay.
more of a chance being stuck in the body and absorbing it.
so we increase the KVP.
Yes.
So if you increase KVP, will your image look whiter or darker?
Think of transmission. What happens with transmission? Or
Okay, fine. Let me step back. Let's do
Yeah.
this one step at a time. If we increase KVP, what happens to the penetrability of your beam?
It'll go through, more will go through when you increase it.
Great, it'll go through more. So more X-rays will go through it, right?
Uh-huh.
As more X-rays go through, will that body part look lighter or darker? Somewhere with more X-rays, is that area gonna have?
It'll be dark.
It'll be more dark. Very good. So, if our goal with bone is to make it look more white,
You have to
do we want to?
decrease it.
We have to decrease it.
Okay, gotcha.
Very good. And so, if you take a look at things like your extremity x-rays, right? You're looking at the bones of the hand or the feet. What are your KVP values? Yeah, they're low, aren't they?
55.
You want the ribs?
Yeah. 50 kVp, 55 kVp, 60 at the most, right? If you're doing chest versus ribs, right? What kind of kVp do you see for your chests?
Like 120.
Like 120. Why is it so high?
It's going
Shooting
through
through.
more tissue.
Right, we want to be able to shoot through the ribs and see the soft tissue behind the ribs, right? We want to be able to see the lungs and the heart. We don't really care so much about the bone. So we're going to shoot through the bone to see the soft tissue. But if we actually want to see the ribs themselves, guess what happens to the KVP?
70
Decrease
kVp.
to like
Right, 70, 75 kVP. Big drop. Increased amount of penetration the bones have, the ribs show up much more clearly. Yes?
The
Jim?
techniques I have written down from Strawberry have it as decrease KVP, but like increase mass. Like,
Increased mass. Correct.
I didn't even know that percent.
That's right. And why does mass have to go up?
Because it's inverse. Well, they have like inverse relationship.
What is that? That's right. What is that rule with KVP and mass? What was the rule with KVP and mass?
No, it's
What, I heard it?
square.
15% rule. If you change your KVP by
15.
15%, mass changes by half, or by 2, right? 2 up or 2 down, right? So if KVP is going down, mass is going up, right? 15% rule, right? So that's why on your ribs you have lower KVP but higher mass.
If KVP is reduced by 15%, mass will go up by 2.
2.
That's a formula.
That's right. Okay, so make sure you know that atomic number and energy both affect the amount of absorption. Because what about scatter? How does energy affect scatter?
Fall.
Cody, yes, what do you think? If energy increases, what happens to scatter?
Doesn't it, in terms to like photoelectric, wouldn't it make like more photoelectric? So like the dose of the patient would go up?
Just asking about Compton scatter.
About
So
something?
you remember that abdomen?
So if you
When we
increase
So would it be
the
fall?
KVP, don't you increase the scatter?
If you increase KVP, I think scatter.
If those are
You
low
gotta be
energy photons, so if you
Yeah.
increase the energy, the scatter.
You increase the scatter.
Yes.
So as KVP goes up,
Yeah.
scatter goes up.
But it's not absorbed.
That's right. So it's the opposite of absorption, right? As energy goes up, absorption goes down, but scatter goes up. All right, so make sure you know that they're different. How about for atomic number? So as atomic number goes up, absorption goes up, right? What about the scatter?
Guess it goes too.
Goes down?
It should go
Goes
down
up.
with the
You
KVP.
sure? With atomic number? What happens to scatter with atomic number as it changes? That's right. No change. Scatter is the same regardless of the atomic number. So it doesn't matter if it's bone or fat or lung, scatter is not going to be changed based on the atomic number. It's still going to be the same. So you cannot see differences in scatter between bone versus fat versus air versus lung, right? You won't be able to see anatomic differences. So you cannot use scatter for contrast. You can only use absorption to create contrast. This part of the body absorbs more, so it's more white. This part of the body absorbs less, so it's more black. That's how you get your image.
And that's that for both types of scatter.
For a continent, for classical, yes, neither of them are affected by atomic number.
It's passed for like that.
Oh,
Text.
okay.
SD,
Oh, Emily?
In the PowerPoint.
So in the, I wouldn't say equation, that's not the right word. In one energy cube, the one represents, if the energy goes up by cube, is cube up, what is the one, what is
It's
that
the
represent?
placeholder for the top. But it's like 1/2 for 1/2.
So it's just like, cause I see it, and I'm like, what is the one?
Anyone have confusion with this?
So if the amount of absorption.
What's your confusion? What are your questions?
Increasing.
So, KBP goes
As in what? The photoelectric absorption? What's your main question? What are your?
He's talking about scatter and absorption and color and the whole thing, and I don't know.
So photoelectric absorption, it deals with with KBP levels, correct?
Yeah.
So the higher the KBP, what happens? What happens to the image? Does it shoot through the body or does it absorb more from the body? You have like higher penetration power. So you think of it, higher KBP, the higher penetration power, right? So the higher penetration
It's been
power
raining.
shoots straight to the body. It doesn't have
It was
time
raining
to
earlier.
absorb in the body, right?
Down that
You
way.
think of absorption in the
It's
body
not
as
raining
well,
right now.
correct? So what happens when it's a lot of penetration? Is
Where
there
did
a lot
you-
of
oh, you
absorption?
$34, I
No? Yeah. So think of absorption and penetration as inverse, right? If one goes up,
literally
everyone goes
tell
down,
go
right?
get my receipt.
I found one control.
I didn't go to Walmart.
Oh, where's it?
I went to Scrubs and more.
Mr.
I went to Walmart, I checked, I didn't like any of them.
This is the same one
I just don't like the way that it fits here.
But it's not as bright.
Kind of big, like here, it stretches a little.
Why did you show me one? They're really
I tried
nice.
this.
I'll show you a picture.
I tried
Once
this.
we get this online.
Right over my clothes.
more there's, more KBP, there's more
And then I went to Scrubs and more, and they're just like, yeah, we got you. So they gave me the same stuff that I
No,
had.
no.
Um,
Less
That's already the
less
less,
white.
the less
Less
white.
white.
So the higher KBP,
Higher penetration, so it's not gonna absorb it, so they lower time to that one.
You held that pressure pretty good.
But if you lower that KBP,
It's intense with them.
it's gonna absorb, the hormone's gonna absorb it, and it'll become one. Yeah.
okay, but what if you talk about the 1/3 and half?
Where's it from?
So.
You need this?
Yeah, it's a lot better than now.
Better than that one?
So if you decrease the energy,
Are you good? I was thinking of it. Yeah, you go ahead.
so decrease the energy by 2, then, no, just decrease it by 2. And you increase the probability of absorption by 3.
Repeat that one more time.
You decrease the energy by half, or by 2.
Are you talking about the KVP to
KVP.
mass? So so KVP, whenever you want to change it, you do the 50% rule, right?
The 1/3.
1/3. We don't. I never seen that on the test or anything.
Talking about that cube.
Yeah, the 1/3.
On the test, I never seen it. So. I wouldn't. Depending how Mr. Phung wants to attack it. Yeah.
I'm still confused about,
What do you decrease it by? Decrease by 2?
wasn't there a equation?
The mass,
No, the KVP.
like the formula, like the KVP.
So the 1/3, yeah.
The 1/3, I don't know what Mr. Phung was with it.
Alright, so let's just make sure that we're all on the same page first. We've got like patient here, we've got the IR down here. Are we okay with this?
Yeah.
Right, so patient.
So
Patient,
can I say this real quick?
go ahead.
Have you guys ever took an X-ray without any anatomy, right? It just shows up black, the iron, when you see it on the image. Well, if you guys ever do that, just shoot up regular, just a plate, it's gonna show up black, correct? Cause why? It's all transmission, right? It just-
Photons are going to the iron.
exactly. There's no absorption happening, correct? So when you see when we do a rib X-ray, you gonna see bone, correct? So that's just showing. Can you show them a picture of the difference
So
between the
you'll
rib?
pass and some won't.
Yeah, exactly. It's just showing you.
Absorb some of
That
the
close your laptop?
Yeah,
Alright.
exactly. Can you show a picture of them, of ribs versus chest? Because that's what helped me when you showed me that one picture.
Damn, he's really good.
Huh?
That's
Yeah.
heartbeat.
I told you, you chose the wrong field. You should have done like
Digital design.
digital design. You would have done it.
He's cheesing hard.
He's flattered. Is it gonna rain today, guys?
Yeah, it was raining down that way.
Is it cold outside or no?
No,
It's not cold.
Not really.
it's 80 degrees outside.
80 degrees. That's what.
It's down by it's cold.
It's humid. It's humid.
It's Texas for you.
That's the perfect nap time.
The solitary setting right now. It's like kindergarten. It's like kindergarten is the solitary setting right now.
I wish.
You
I'm
taking naps
struggling to
in
stay
the
awake right
lounge
now.
room, huh?
My eyes.
I thought you were like studying like this, but when I got closer, you're just like.
I'm not paying attention.
I was studying and then.
Exactly, we go.
That's how you fall
Did you see me over there laid out like?
I retain that information.
Like, that's I can't deal with that.
Yeah, but see, this is what I did this weekend, not this sheet, not this sheet. Like this, I wrote my things like, not that right there. Yes, I wrote it like word by word, look at the video. So Mr. Phung, right now we're talking about photoelectric absorption.
The more absorption that happens, the brighter the white looks, right?
Yeah.
If you took a picture of a metal plate, it's gonna look really bright on the image, right? Compared to a bone. Because why? Higher atomic number and the more absorption in there. Does that make sense?
Yep.
So the more absorption it is, the brighter the white looks. Have you guys been to bone clinic and you guys see like a metal piece in the femur or on the arm? You can really see the metal light up a lot brighter than the bone, right?
Like the hardware.
Yeah. So out of those two examples, which one has more absorption, the metal or the bone?
The metal.
Metal, right? You can tell by because it's
like really.
it's a lot more brighter.
All right.
So this is a perfect image that helped me a lot trying to figure out the difference between the absorption levels. So go ahead, Mr. Phung.
Okay, so tell me, what do you see as the difference between these two?
Okay, you can clearly see the ribs and all the bones and stuff better on the right one.
Okay, so the right one, you say the ribs show up better,
Yeah.
and then on the left one,
Kind of like foggy.
right, it's not as clear, right? It looks more white, more gray, right? More, it's less obvious where one thing ends and where the next thing begins, right? So this is what we call contrast, right? The word contrast, what does it mean?
It's like a white line.
It's white.
It's
Right.
very
Great difference between white and black, right? How easy it is to tell two things apart, right? Based on their colors. So something has high contrast, it's obviously white, obviously black, right? If something has low contrast, you've got like black, dark gray, gray, light gray, right? Whitish gray, white. So it's gonna be less obvious where one color starts and the next one begins. So when you have a high amount of photoelectric absorption, right? That means it's either gonna be white or it's gonna be black. It either transmitted or it absorbed, right? There's not gonna be something where half transmitted, half absorbed. It's either one or the other. So on the right side, that is what we see more of. The bones are absorbing more X-rays, so they show up more white, right? And go ahead, Jalen.
I have another. If you can look on the spine, as you can see, you can really identify the separate blocks, right? Because it's being a lot more absorbed. This is the rib image, just to let you know. It's being a lot more absorbed. But if you look at the higher KVP, you can see it just kind of fogs all in together.
Right, because now it's a mix of like your soft tissue, it's a mix of your bone, like going through the bone. So it's not gonna be as clear. Right? So, right side, higher absorption, lower KVP. So right side here is low KVP. Over here, your chest, this is less absorption. This is gonna be higher KVP. Okay, so that's the difference between these two images.
Mr. Phung?
Yes.
I might have missed this because I just stepped out, but if, let's say GSW comes in and we know, do we lower the exposure like the normal slightly to make sure that we can get all of the,
No, leave it as your normal chest exposure.
Okay.
Like on the chest, you can still kind of see the ribs, right? But on a GSW, more than the ribs, you're interested in lungs and heart,
Okay.
right? Because you want to see, is there pneumothorax, right?
Okay.
Or is there pleural effusion? So leave it as your normal chest.
So the left one, it's really white, so isn't that less KVP?
So the white one, sorry, the left one is actually higher KVP. So the,
Yeah, you see it's like blurry.
right, so the brightness, the overall brightness, right? That's not what you really want to use to judge. The reason is because you're trying to make the brightness about the same by changing your KVP and your mass. Right, so yes, you raise your KVP, you have more penetration, right? But at the same time, you're lowering your mass. So it's not that it's going to be more white or more black. It should look about the same whitish blackish. What changes is the contrast. Will the tissues be more obviously one or the other, or is it going to be more similar? The higher the KVP, the more penetration we have. So the more penetration we have, the more we can see everything, but the more similar those things may also look. Let's see. Okay, that's confusing. So let me just try and show you here. Let me just try and show you over here.
I thought I had it, now I don't.
So yes, go ahead, Charlie.
Okay, so if you want to increase the amount of absorption, right?
Yes.
You would increase the KVP. You would decrease the KVP by so let's say I'm just gonna use it in number terms.
Okay.
If I change the amount of absorption by 3, I would decrease the KVP by 3 cubed. Is that?
No, it's the other way around.
So you would increase it.
No, it's absorption is what changes by the cubed amount.
Okay.
Absorption changes by the cubed amount.
So that's what I was asking when I said 1 and energy 3. So it's the absorption that's cubed, and if you change the energy, the absorption goes up by the cubed amount.
Correct.
So if I change the energy by 2,
No.
the absorption goes
Or
up.
sorry, go ahead.
If I change the energy by 2, the
Yes.
absorption goes up by 8.
Yes, that is correct.
Thank you. That's where I was confused about.
Alright, so let's say that we've got some x-rays here. Alright. Alright, x-rays coming into the body, right? What kind of beam is this? Right, primary beam, right? Okay, so over here, lungs. Will lungs have high absorption? No, right, mostly, so x-rays are gonna pass through the lungs. Okay, no problem. Okay, over here, lungs. Will this area have high absorption? No, x-rays are gonna pass through these lungs, right? Alright. And so when these x-rays hit the IR, right, this part is gonna get dark, right? We're gonna darken up this part of the IR. Right? This is all the area that's being hit. Okay. What do we have here in the center? Spine. Right, so x-rays come through and they hit the spine. Alright, spine is made of what? Bone. What else? So what's gonna happen here? It's gonna be absorbed, right? So not much darkness, right? So these areas are gonna be dark. This area, not so much. So you have a big difference between these two areas, right? We're gonna have high contrast. As we raise the KVP, right, as we raise our penetrability, is this gonna be highly affected?
No.
Are we gonna see more penetration here?
Yes.
Well,
Yes.
technically, yes.
Technically, yes, right? But most of them are already going through, correct? So it's not really gonna change this area too much, correct?
Yes.
But what about the spine?
That'll change a lot.
All right, we're gonna get more penetration here to spine. So this area is going to get darker now, correct? So these two areas are gonna look more similar, correct? And then, what we end up doing is we end up reducing the mass. Right, so then we end up dropping the mass, and so we have fewer X-rays coming through. And so, rather than the image looking darker because of all this extra penetration, right? The image now looks the same again. It looks the same brightness because we've reduced our mass at the same time that we increased our KVP. So we're maintaining the intensity. We're still getting the same number of X-rays on average to the IR. But you're getting more X-rays through where the bone is. So now the bone is gonna start looking a lot more similar to your soft tissue. You're not gonna see such big differences between your bone and your soft tissue because now both of them have less absorption and have more penetration going on. And because they look less different, right, that means both of them are gonna be looking kind of more white. Right, their colors are gonna be a lot more similar. Right, you compare that, so if we go back to our thing here.
So picture with the
You were right.
No, I feel like a bug is like in my ear.
Like all the way around, so why would you always
Just shake it off. Shake.
I seen him jerking.
They see on TikTok?
Alright, so then you compare this back to here, right? So you see that the bone, the color of the bone here looks more like your soft tissue here, right? Because it's penetrating both of them a lot more. So bone and soft tissue, they're gonna look more similar. The brightness won't be as different, won't be as obvious. Over here, bone is absorbing more, soft tissue is absorbing less, so the differences between them are more obvious.
So that's the contrast.
So that's the contrast. So you have higher contrast on your ribs compared to your chest. Now I think there's a question, why not just use the right side all the time? Right, because it looks better. Right? But take a look up here, for example. Do you see how we're actually burning out the lung markings? Like you can see the lung markings here, but you can't see them over here, right? It looks more black.
So left is still considered more optimal?
No.
So depending on what we're looking for,
the example.
Like for the chest exam, I mean.
right, so if you're looking for lung markings, you want this one because this shows the soft tissue better, right? If you want only bone, then you want this one. Soft tissue doesn't show up as well anymore because you don't have as many colors to show it with. Your contrast is higher, but you can see the bone a lot more clearly. So it all just depends on what the doctor is looking for. If they're looking for bone, you want this because this shows bone. Soft tissue, not so much. If you want soft tissue, you want this. Doesn't show bone as great, but it shows soft tissue a lot better.
So if you were looking for a fracture, you want that one.
Correct.
If you were looking for a pneumothorax, you would want that one.
Correct.
So if you're looking for fluid, you would still use this one?
Correct. You use the chest for fluid. High KVP for fluid. For soft tissues.
Like today?
Yeah, it's 10, 24, 22.
Well, it's the
One
lungs
point.
that are affected by the fluid. Lungs are soft.
45.
Yeah, but you're looking for
So you just searched up
Mhm.
ribs and look good.
Yeah, the most recent. It was taken today. And the phone was taken too.
If you,
On the 17th. at 2
so
a.m.
if you're concerned about fluid affecting your image, right, you would change your mass,
You can see.
not your KVP. Because you want to keep the same contrast. You want to keep the ability to see soft tissue. But if you're worried that the fluid is going to need more X-rays, right, higher exposure technique to demonstrate the fluid, you raise your mass, you raise the number of photons. It won't change the penetration, so soft tissue still shows up properly, but you will be able to shoot through the fluid a bit better by raising that mass. All right, so make sure you understand absorption versus scatter. Absorption is what creates our image. Scatter is what destroys our image.
So absorption has to do with the contrast between bone and soft tissue, and scatter
Correct.
creates fog, right?
Correct. Scatter keeps you from seeing that contrast. Yes?
Are
Kate?
there specific, or are there ways for us to visualize different types of scatter? Like, let's say, an area being burnt out specifically, or being fogged, or like blurred, or is that just too?
Okay. So, with scatter specifically, so scatter is a very specific word, right? So,
Okay.
for example, burnt out. Burnt out would not deal with scatter. Instead, if you have an area that's burnt out, one of the things that we discussed was using something to reduce the number of X-rays reaching that area.
Filtration.
What kind of filtration?
Compensating.
Great, so we could use compensating filtration to reduce anatomy that gets burnt out so that it shows up more properly. Or if you don't have filtration, what else could you try and make use of?
Anode Hill effect.
Anode Hill effect. Great, so with anode Hill effect, where would you want to put the burnt out anatomy? Carmel, what do you think? With the anode Hill effect, if you shoot like a foot X-ray, and you're like, oh no, the toes are burnt out, where should you try and put the toes next time to keep them from being burnt out? Closer to the anode. Anode gets fewer X-rays, so it won't burn out as easily. Okay. Fog. So yes, with fog, we use grids or the air gap technique to reduce fog. You're not going to be able to differentiate between Compton scatter and classical scatter. All scatter is scatter. Okay. Scatter is just any radiation going in a different direction than originally. Okay, so you can't differentiate between them, but it will ruin your image, so we use things like grids to remove as much as we can. And then blur. Blur is not fogging. Blur happens when you have anatomy that is expressed over a large part of your IR, so the edges don't look sharp.
Okay.
So what two things affect blurring? It is going to be your focal spot. Your focal spot affects blurring. And then your magnification or your SID. So magnification also affects blurring. But some of those are more advanced topics, so we won't worry about them too much right now. Okay. But that's ribs versus chest.
Pretty easy, right?
Any gold star questions you can just throw at us real quick?
Any gold star questions I can throw at you?
Pertaining to.
As KVP goes up, what happens with the absorption? Does it increase, decrease, or it stays the same?
Decrease.
Yeah, and then vice versa. And then
Hair production already? Love it.
All right, so are we okay with Compton versus photoelectric?
Yes.
Compton and photoelectric are going to be your two big ones in X-ray. Classical and the two we're about to talk about, hair production, photodisintegration, and but Compton and photoelectric is where the main meat of your stuff is going to come from.
Can you go back to photoelectric? There was like some kind of, what is it called? Equation or something?
The 1 over energy.
the one over
No,
there.
no.
No, it's in.
This one?
Yeah.
Oh yeah. Is that relevant or no?
I didn't go over that.
So this is just like we talked about, this is very similar to what we talked about in Compton. Remember, Compton or photoelectric doesn't matter. Photon comes in, knocks out the electron, right? Main difference is, what kind of electron does Compton knock out?
Oh, no.
Compton?
Outer shell.
Outer shell, great. What does photoelectric knock out? Inner shell. So, outer shell, high or low binding energy? Low. So photon comes in, gives it some energy, about 1/3, knocks it out. Photon still has plenty of energy remaining to keep going, right? Photoelectric, high or low binding energy? High. Photon comes in, uses all its energy to kick out the electron. Now, the photon might have more energy than the binding energy, right? So it used up some of its energy to kick it out, but what happened to the rest of it? Right, it gives the rest of the energy to this electron. So this electron has energy when it leaves. Right? It doesn't just leave without any energy at all. It leaves with energy. How much it has depends on how much the photon gave it. It's a lot like, anyone play pool or billiards or whatever?
Yeah.
So
Billiards.
you hit
It's
the
the same name.
you hit the cue ball, right? Cue ball hits another ball. What happens to the cue ball?
Depends on the English.
All right, let's say you hit it dead on.
It'll probably stay there.
That's right. The ball stops, right? It doesn't bounce off. It doesn't run off anywhere. It stops right there. It transferred all its energy to the next ball, right? So same thing. Same thing here in photoelectric, right? Photon comes in, transfers all of its energy to that electron. How much energy does the electron have? All the energy the photon gave it, minus what it needed to leave. What did it need to leave?
The binding energy.
The binding energy, right? That's the toll it had to pay to leave.
250.
Right?
253.
So I'm living here. Guy comes over. It's like, all right, I'm paying you to leave. Like, all right, get my 10,000. It's like, my landlord's like, no, you signed a contract with me. You break the contract, you gotta pay. So it's like, all right, doesn't matter. I'm out. Here's your 100. I'm gonna leave the rest of the money, right? So it's the money I was given minus the money I need to pay in order to leave, right? Money I was given, energy I was given, minus the energy it needs to leave. That is how much energy the photoelectron has. And what is the photoelectron? Great, electron that got knocked out, the one that leaves the inner shell. Okay.
And when you go over the, or which one was electric volts again?
Which one was what?
Just EV?
EV, yes. So, right, photoelectric happens in the 20 to 120 kVp range, but when we have our
It's still photoelectric.
characteristic cascade going on inside photoelectric absorption, the photons released are going to be really low energy.
So it's still within photoelectric?
Mhm.
Okay.
Okay. Any other questions?
And then the next
EVs.
part is saying the probability that
electrical.
Voltage.
Yeah.
would happen.
Correct. So I want you to compare this with this. Right, those are the two slides I want you to be able to compare. Look at this and be able to compare it to this. What do you notice?
It's not dependent on the atomic number.
Not dependent on atomic number. What do you notice?
Dependent on KVP.
How is it dependent?
Higher.
That's right. Higher energy means more Compton, less photoelectric, right? Higher energy means more Compton, less photoelectric.
Also, in the scattering, it's photons, right? And in the photoelectric, it's electrons that.
Both of them release photons and electrons.
Like,
Until he explains something.
So, what leaves the atom in Compton scattering? What are the things that leave the atom in Compton scattering?
The electrons.
What electron?
The outer shell.
Okay, great. Outer shell electron leaves. What else leaves, Shamika?
A photon, the second.
Great, the photon, right, your secondary, your scatter, right, your Compton photon, right? So you have two particles leaving with Compton scattering, right? One electron, one photon. Okay, what leaves the atom during photoelectric absorption? Let's see. So, mhm. So yes.
What is that?
What link
So the electron leaves, like, it gets kicked out,
So what electron leaves in photoelectric absorption?
the orbital electrons,
Which orbital electron?
the one near the cation.
Okay, so the inner shell orbital
shell.
electron leaves. Very good. So photoelectric, we have an inner shell electron leave. What do we call that inner shell electron once it leaves? That's right, that is our photoelectron with the ejected electron. What else leaves the atom, Jay? What else leaves the atom during photoelectric absorption? Is it just the photoelectron?
No, it's energy.
Energy, great. Where does that energy come from?
The initial photoelectron, and then it's
The energy that leaves the atom, where does it come from?
oh, I'm sorry. It's from the transference of patient or from shells.
Great. So what do we call that?
Cascade.
Great. It comes from our cascade, right? So we also have photons that are leaving the atom, created by our cascade.
Those are the secondary photons?
Right. Those are our secondary photons. Okay, do we have the animation here? Yes. Okay. Right. Animation. Right. The electron and, as we can see, are secondary photons as well, right? So, both Compton and photoelectric have an electron leaving and photons leaving. The difference is what kind of electron and what kind of photons, right? Where did the photons come from? Where did the electron come from? So make sure you can explain those differences. Does that make sense?
Yes.
All right, so. Only one yes, all right. Guess we're gonna have to ask a few more questions to make sure.
Okay.
All right, so John's.
Moving on three.
All right, John's. Compton scattering.
Just take a
What
deep
kind of
breath.
electron are we dealing with? What kind of electron leaves the atom?
Scatter and transmission.
So Compton scattering, what electron leaves the atom?
Oh, the cation. Is it
For
just-
Compton scattering? So Compton, not photoelectric, but Compton. Which electron leaves the atom?
Like from the shell, like on which shell, which electron gets knocked out?
Nah, dog. Yes, you
You know this. We went over it multiple times.
Inner or outer?
Yeah,
So
sink or swim,
Oh.
homie.
The outer? Because photoelectric is right.
Get your lifeline, man. We here.
I
All
did,
right,
but
it's
clearly
3
the
o'clock.
lifeline didn't want to-
We'll go ahead and end here, but you